Hi, this is Dr. Jivikas Paul. In this session, we'll discuss about the deflection of cantilever beam with point loaded free end and UDL as well as UVL using double integration method. Uh, Next. So, in the first case is cantilever beam subjected to point loaded to free end. So, here we need to find the slope at B and deflection at B by using double integration method. So first of all, we need to consider a section XX between A and B at a distance of x from B. So at this point, we need to calculate the moment. So from differential equation, we have m equal to E at d square by dx square. So mxx is equal to, if you see the right side, it is w into x is the moment. So right side clockwise is minus. So mxx equal to minus wx. These are the sign conventions. So equating 1 and 2, ei d square by dx square equal to minus wx. So integrating this equation 3, we will get ei dy by dx equal to minus wx square by 2 plus c1 constant. Now how to find this constant c1 using boundary conditions? So this is the original beam, this is a deflected beam, theta b, yb or y max we need to find. So x is distance from B. So x equal to 0. That means at B, theta is theta B, y is y max. And x equal to L. That means at A, theta is 0, slope is 0, deflection is 0 at A because it is fixed support. So at A, x equal to L and theta equal to 0. That is dy by dx equal to 0. This is the first boundary condition. So substitute this in equation 4. So here you will substitute x equal to L and here 0. Then we will get C1 value as minus WL square by 2. Substituting C1 value in equation 4, we will get slope equation. So to get slope equation. So this is the slope equation. Now integrating this equation, we will get this one. dy by dx becomes y and this. And constant C2 will come. At A, the boundary conditions to find C2, we need boundary conditions. So at A, x equal to L, y equal to 0. So I'll substitute this one here in this equation. So 0 here and L here. I will get this one. So C2 value minus WL cube by 3. So I will substitute here in equation 6 to get deflection equation. So I got deflection equation after substituting. To find slope at A, now we got deflection equation, slope equation. Now we need theta B and YB. So to find theta B, substitute x equal to 0 in slope equation. To find YB or Y max, substitute x equal to 0 in deflection equation. So to find slope B, theta B, substitute x equal to 0 slope equation. That is equation number 5. So here if I substitute x equal to 0, I will get theta B. So theta B we got it as WL square by 2EI. So theta B is WL square by 2EI. To find deflection at B, I will substitute x equal to 0 in deflection equation, that is 7th equation. So I substituted x equal to 0 in 7th equation number 7, yb equal to minus WQ by 3a. So these are the slope and deflection at B, support B. In the same way, we can calculate for cantilever beam subjected to UDL over the entire span. So here the moment is W into x by 2, wx square by 2, right side clockwise, so minus wx square by 2 will come. W into x is a load and it acts as a center, that is x by 2. So this is a moment. Ei d square by dx square equal to minus w square by 2. This is the first equation, and if we integrate this, we'll get constant c1. And applying the boundary condition x equal to L, theta equal to 0, and same pressure, we'll get c1 value. Substituting c1 value here, we'll get slope equation. And then integrating the slope equation, we will get one constant c2. To find this c2, we will apply another boundary condition x equal to L, y equal to 0. So I substitute here x equal to L, y equal to 0 in the above equation. Then I will get c2 value. Substitute c2 value in equation number 4. I will get deflection equation. Then substituting x equal to 0 in slope equation, I will get theta b. And substituting x equal to 0 in a deflection equation, I will get a yb or y max. So these are the values, WL cube by 6ei and minus WL power 4 by 8ei. In the same way, we can calculate the deflection on the slope for cantilever beam subjected to uniformly varying load over entire span. So here this is a UVL. So consider a section XS between A and B. So I have taken a section at a distance of x from B. Okay, now at this point I need to calculate the moment. See here, let this height be y and this is x, this is w and this is l. Now how to find y? From similar triangles we can write w by l equal to y by x, w by l equal to y by x. From here y equal to wx by l. Now y is wx by l and this is x. Okay, now how to calculate the moment at this point? Mxx is equal to, so area of triangle, half into x into y, that is half into x into y, half into x into y, okay, into half into x into y is the load and it acts as a centroid. This, what is the centroid distance here? Centroid distance is x by 3. This is x by 3. Okay, so into x by 3, force into perpendicular distance. Force is area of triangle, perpendicular distance is x by 3. Okay, so from here if I substitute y equal to wx by l, I will get this one. So this is the equation number 1. If I integrate one time, I will get c1. Then if I integrate again, I will get c2 also. Then if I, to find c1, I will substitute x equal to l, theta equal to 0. And when I substitute, I will get c1 value. If I substitute c1 value in equation number 2, I will get equation number 2, I will get a slope equation. And I will substitute x equal to l, y equal to 0 in equation number 3. Equation number 3, I will get this one. I will get the value of c2, and substituting c2 value in equation number 3, I will get deflection equation. To find slope at b, I will substitute x equal to 0 in slope equation. To find y b, I will substitute x equal to 0 in deflection equation. Let us see a problem on cantilever beam subjected to combination of loads using Macaulay's method. A cantilever beam 2 meters long carries a UDL of 10 kN per meter over 1 meter portion from fixed end and point load of 20 kN at free end. Calculate maximum slope and deflection at cantilever using Macaulay's method. So at B, we need to calculate theta B and yb. This is the deflection curve. So theta B we need to calculate and yb we need to calculate. So mxx equal to EID square over dx square. Now what is mxx? Moment at any section. See here in Macaulay's method, we need to take a section xxx such that everything is covered, all the loads. So at a distance of x from B, I have selected this section. Okay. Now at this point, I am calculating the moment to the right side. Okay. So 20 into x minus right side clockwise. So minus 20x minus, so this length is x minus 1. So this total is x, this is 1. So this is x minus 1. Okay, this is x minus 1 and it is acting at exactly at the center. So x minus 1 whole square by 2. So 10 into x minus 1, see 10 into x minus 1 whole square by 2. 10 into x minus 1 is the load here. Yeah, so integrating this equation, we will get this equation in terms of C1. So what are the boundary conditions here? At A, that is x equal to 2 meters, slope is 0. So substitute x equal to 2, theta equal to 0 in this equation. I will get C1 equal to 41.6. Substitute C1 value here, I will get a slope equation. Now, so this is the slope equation. Again if I integrate, I will get EI y equal to this one. C2 I will get. Now I will apply another boundary condition, that is x equal to 2 meters, y equal to 0. Means at A, deflection is 0. So if I substitute this in equation 4, I will get the value of C2. So substituting C2 value here, I will get deflection equation. Now to find theta b, I will substitute x equal to 0 in this equation, slope equation. So I will get theta b, theta max value, and for theta b I will substitute x equal to 0 in deflection equation, that is equation number 5. I will get the y value also the same way. In the same way we can do for overhanging beam also. Overhanging beam problem. Find the support slope at support. So slope and deflection free end for the overhanging beam shown in the figure. So we need to find slope at supports, that means theta A, theta C we need to find, and at free end also, that is at D. Suppose this is D, we need to find theta D and YD, deflection at free end. So theta A, theta C, theta D and YD we need to find. For that, first of all, we need to find the reactions Ra and Rb. So using sigma ma equal to 0 and sigma fy equal to 0, I can find the reactions Ra and Rc. See, sigma ma equal to 0 if I do. So 5 into 5 minus 4 into Rc, Rc into 4, distance is 4, plus 4 into 2 is a load into 1. So here we can get Rc, and using sigma fy equal to 0. So Ra plus Rc equal Ra sigma fy equal to 0. So Ra plus Rc equal to 4 into 2 plus 5. In that way we can find Ra. From Macaulay's method, this is the equation. And then mxx, that means here I have taken xx section like this. From A it is x. Okay, now at this point I need to calculate mxx. So 4.75 into x minus 8, that is 4 into 2, 8 into x minus 1, and then yx minus 1, because it is 2, it is acting at center. So this is x minus 1, this distance is x minus 1, plus 8.25 into rc into x minus 4, this is x minus 4. So integrating one time we will get ei dy by dx, other time we will get ei by. Here the boundary conditions we need to use is x equal to 0, y equal to 0, x equal to 4, y equal to 0. Using this we can find c1 and c2 values, and substituting in the slope and deflection equations we can find the slope equation and deflection equation. And now to find theta a, after getting slope and deflection equations, to find theta a we will substitute x equal to 0. To find theta c we will substitute x equal to 4. To find theta d we will substitute x equal to 5. To find yd we will substitute x equal to 5 in deflection equation. To find theta we will substitute these values in slope equation. To find y deflection yd we will substitute x equal to 5 in deflection equation. Okay, the x is the distance from the A. Okay, right. Thank you.